In this video, we're going to start the notes and examples in section 1.7 on limits and continuity. So in our class so far, we've seen the notion and idea of a limit, but now we're going to get into continuity, which is related to how graphs look and a feature of a graph. So just looking at these two graphs, you might notice that there's a point sort of highlighted. Here's a point, extra point outlined on our graph in that first example. And then in this second graph, we have the point at x equals a up here on our graph. So what observations might we make about the continuity of one graph or the other? Just some intuitive idea. So we see at this first graph, I can draw with my pen all the way along it without ever having to lift up my pen. Well, in this second graph, if I were to trace it over as best I can, I have to lift up my pen right here to draw the output at x equals a and then continue. So in this way, the second graph is not continuous at this point, x equals a. So let's write down some of the language we use to describe both of these graphs. So we'd say in this first graph, this graph is continuous at x equals a, while the second graph is not continuous at x equals a. So we just intuitively determined these conclusions, but how would we mathematically show or justify if a graph is continuous or not at a point? Well, to do that, let's look at the following definition. So in mathematics, there are three conditions that must be set or satisfied in order for a graph to be continuous at a point. So let's read this definition together. So we say a function is continuous at a if the limit as x approaches a of f of x is equal to f of a. Meaning as we approach a from either direction, then the function value is equal to the limit. So graphically, continuity means that f has no breaks or jumps at x equals a. In particular, if f is continuous at x equals a, then the following three things must be true. So essentially, this statement here, this equality, means three things. What does it mean? First of all, that the value f of a must actually exist. Our graph must be defined there. Second of all, the limit must exist. So we can't have something like a graph like this. We would say graph is not continuous at that point a because the limit does not exist as we approach x equals a. So that's like a non-example. And then lastly, the limit as x goes to a of f of x must equal the output value itself. So non-example here would be the example we saw in the first graph, or that second graph on the right. The limit as x approaches a does exist, but f of a up here is not equal to the limit. So just to recap, we looked at these three conditions that must be satisfied or met in order for a graph to be continuous at a point. If a graph is continuous everywhere on its domain or on the where the input values are, then we say that the function is continuous. In the next videos, we'll look at some examples for how to check if a graph is continuous at a point. Thanks for watching.